On December 9th, 2024, a team of astronomers led by Nobel Prize-winning physicist Adam Riess released a result that sent a quiet shockwave through the entire field of cosmology. Using the largest sample of James Webb Space Telescope data ever collected for the purpose, more than 1,000 pulsating stars observed across dozens of distant galaxies, Riess and his colleagues confirmed something researchers had spent nearly a decade hoping was simply a mistake. The universe is expanding faster than the standard model of cosmology says it should, and the discrepancy is not going away. If anything, it was getting harder to explain. For years, scientists comforted themselves with the possibility that faulty instruments, overcrowded star fields, or some subtle calibration error were quietly distorting the numbers. Webb was supposed to be the telescope that finally settled the argument, one way or the other. Instead, its data lined up almost perfectly with measurements from the older Hubble Space Telescope, closing the door on the easy explanation and opening a far more unsettling one. Something about our fundamental understanding of the cosmos, its age, its structure, and quite possibly its ultimate fate may be wrong. And in the years since that announcement, Webb has continued turning up discoveries that seem to confirm just how strange the true picture might be. To understand why this single number matters so much, we have to go back almost a century to the late 1920s, when American astronomer Edwin Hubble, working at the Mount Wilson Observatory in California, noticed something that shouldn't have been possible under the physics of a static, unchanging universe. Distant galaxies were rushing away from us and from each other, and the farther away a galaxy was, the faster it appeared to be retreating. This simple observation implied that space itself was stretching, carrying galaxies along with it like dots painted on the surface of an inflating balloon. It was the first solid evidence that we live inside an expanding universe, and it eventually became the foundation for the modern Big Bang model. But it also revealed something uncomfortable, that the vast majority of the universe was, and still is, completely invisible to us. If you shrank the entire cosmos down to the size of a house, everything humanity can directly see or touch, every planet, star, and grain of sand would fit inside a single small room. The rest of the house would remain dark, governed by forces we still don't fully understand. Over the following decades, researchers including Vera Rubin, Saul Perlmutter, Brian Schmidt, and large international collaborations behind missions like the Planck satellite and NASA's WMAP observatory pieced together a working model of what fills that dark, invisible majority of the house. Ordinary visible matter, the stuff that makes up planets, stars, and every living thing, accounts for only around 5% of the total universe. Roughly 27% is dark matter, an invisible substance that never interacts with light, but exerts enough gravity to hold galaxies together, preventing them from flying apart as they spin. The remaining 68% is dark energy, a mysterious property of space itself that appears to be actively pushing the universe apart, accelerating its expansion rather than slowing it down. To measure exactly how fast that expansion is happening, scientists rely on a single figure known as the Hubble constant. And to calculate it, they developed two completely independent methods that, in theory, should arrive at the same answer. The first method looks toward the deep past. It relies on the cosmic microwave background, the faint afterglow of the Big Bang itself, light that has been traveling through space for roughly 13.8 billion years. The Planck Space Telescope spent years mapping this ancient radiation across the entire sky, charting incredibly subtle temperature fluctuations that represent the seeds of every galaxy that would eventually form. By comparing this pattern against a detailed physical model of the universe, one that accounts for gravity, the density of matter, and the influence of dark energy, researchers can tune that model until its predictions match what Planck actually observed. Once the fit is right, the model spits out a single number for the universe's current expansion rate. That number comes out to roughly 67 to 68 kilometers per second for every megaparsec of distance, a megaparsec being about 3.26 million light years. In practical terms, that means for every additional megaparsec separating two galaxies, they are drifting apart from each other roughly 67 kilometers per second faster. The second method takes the opposite approach, measuring the expansion rate directly in the nearby present-day universe, using what astronomers call the cosmic distance ladder. This technique relies on a careful chain of measurements, each one calibrated against the step before it. Astronomer Adam Riess, leading what's known as the JWST project, has spent much of his career refining this ladder into one of the most precise tools in modern astrophysics. The first rung relies on a special class of pulsating stars called Cepheid variables, whose brightness rises and falls in a rhythm directly tied to their true luminosity. Because scientists know exactly how bright these stars really are, comparing that to how dim they appear from Earth allows for an extremely precise distance calculation. From there, Cepheid variables are used to calibrate a brighter class of exploding stars called type Bia supernovae, visible across even greater distances, extending the ladder out across the observable universe. For years, this work relied heavily on the Hubble Space Telescope, and its results consistently produced a noticeably higher number, around 73 kilometers per second per megaparsec, roughly 5 to 6 kilometers per second higher than the value derived from the ancient cosmic microwave background. At first glance, a gap of 5 or 6 units might not sound alarming, but in cosmology, it represents a difference of roughly 8 to 9% between two independent, highly precise methods, an enormous gap for a field built on exacting standards. Imagine two doctors weighing the same patient on properly calibrated scales, one getting 154 pounds and the other nearly 168. When both methods are sound, the discrepancy stops being about the numbers and starts raising a deeper question: why are two trustworthy measurements of reality disagreeing? This is precisely the situation cosmologists have found themselves stuck in for more than a decade, a standoff scientists have come to call the Hubble Tension. For years, the last comfortable explanation available to researchers, including Riess himself, was the hope that the discrepancy stemmed from some hidden flaw in the Hubble Space Telescope's instruments, perhaps overcrowded star fields blending together and skewing the brightness measurements of distant Cepheids. That hope is why so much scientific attention turned toward the James Webb Space Telescope once it became operational. With its enormous gold-coated mirror and extraordinarily sensitive infrared instruments, Webb can cut through obscuring cosmic dust and resolve individual stars with a clarity no previous observatory could match. NASA pointed Webb at many of the same galaxies and the same Cepheid variables that Hubble had already studied, and astronomers widely expected this cross-check to finally resolve the mystery, either by confirming a hidden systematic error or by validating Hubble's numbers outright. The results, published across 2023 and again in that pivotal December 2024 study, turned out to be genuinely stunning. Webb found no meaningful errors in Hubble's measurements. Its independent observations confirmed, to a confidence level of 8 standard deviations, that the local expansion rate really is close to 73 kilometers per second per megaparsec. The instruments were not the problem. The 9% discrepancy was, and remains, entirely real, and that transforms the Hubble tension from a technical curiosity into a genuine crisis at the heart of modern cosmology. It suggests the universe is not expanding the way our standard model, built on Einstein's theory of general relativity, predicts it should. Something fundamental appears to be missing from the picture, and the harder scientists try to reconcile these two measurements into a single, consistent story, the more convinced many of them become that the problem runs deeper than the expansion rate alone. Because tucked inside this discrepancy is an even more unsettling implication involving time itself. Under the standard cosmological model, calibrated using data from the Planck satellite, the universe is calculated to be approximately 13.8 billion years old. But if the local present-day measurements championed by Riess and his team are the more accurate representation of reality, then some cosmologists argue the universe's true age and its detailed expansion history may need meaningful revision, potentially reshaping our timeline of the universe's early growth by hundreds of millions to more than 1 billion years, depending on which resolution to the tension eventually proves correct. On a human scale, that difference seems abstract, but on a cosmic scale, it hints that the entire evolutionary path of the universe, how quickly the first stars ignited, how rapidly galaxies assembled, may have unfolded differently than the textbook version that most of us grew up with. And if our understanding of the universe's past expansion is this uncertain, it naturally raises the unsettling question of whether we can trust our predictions about its future. Cosmologists, including researchers like Katie Mack, who has spent much of her career studying the far future of the cosmos, note that if dark energy continues behaving the way current models suggest, the most likely ultimate fate of the universe is a scenario often called heat death. It may be the coldest, most merciless ending physics currently allows. Over tens of billions, and eventually trillions, of years, space will keep stretching. Galaxies will slip past the cosmic horizon one by one, permanently vanishing from each other's view as the light connecting them simply never arrives. Stars will burn through their remaining fuel and wink out, and without fresh clouds of gas dense enough to collapse into new ones, none will ever replace them. The once brilliant universe will fade into a vast, near-empty darkness, its remaining scraps of matter separated by distances so enormous that even a chance meeting between two stray atoms becomes an almost impossible event. Under this scenario, the very concept of time eventually loses meaning, because nothing is left that could change. But to understand where the universe might be heading, it helps to look back at how strangely it may have behaved near the very beginning, and Webb's observations of the earliest galaxies have been just as disruptive to established theory as its confirmation of the Hubble tension. During one of its deepest surveys, Webb captured light that had been traveling toward us for more than 13 billion years, a signal originating from an era when the universe itself was only a few 100 million years old. In that single deep field image, researchers cataloged roughly 45,000 galaxies stretching across the depths of cosmic time, many appearing as nothing more than faint, reddish points of light. That reddish tint is itself meaningful. It reveals that the light from these galaxies has been stretched toward the red end of the spectrum by the expansion of space, confirming that we are looking at objects sitting at almost unimaginable distances, some already in existence a mere 600 million years after the Big Bang. What caught the attention of researchers like Seiji Fujimoto and his colleagues wasn't just how distant these objects were, but how unexpectedly bright some of them appeared, far brighter than anything that should exist so soon after the birth of the universe. The obvious first guess was that these were simply the earliest galaxies caught in the act of forming, chaotic and bursting with new stars. But galaxy formation is a gradual process. Primordial gas has to cool, collapse under its own gravity, and cycle through multiple generations of star formation before producing a galaxy bright enough to notice from billions of light years away. And that process should take far longer than the few hundred million years available. Making matters stranger, mass estimates for these so-called little red dots suggested they were, on average, hundreds of millions of times more massive than our Sun, an enormous amount of mass concentrated in objects that, by every conventional model, simply shouldn't have had time to grow that large yet. Further analysis by researchers, including astrophysicist Pablo Arrabal-Haro, revealed something telling about the light from one particular object among these little red dots. Rather than escaping cleanly into space, the light appeared to bounce repeatedly inside a surrounding shroud before reaching Webb's instruments. Researchers proposed that this scattering effect was caused by an extraordinarily dense cocoon of partially ionized gas and cosmic dust enveloping the object, thousands of times denser than the environment found in a typical galaxy. As light tries to escape through that shell, it gets absorbed and re-emitted over and over, losing its direct path outward. This led scientists to a striking hypothesis, that hidden beneath this dusty veil sits one of the most violent objects the universe can produce, a quasar. Picture an enormous supermassive black hole, similar in scale to the fictional Gargantua from the film Interstellar, then multiply its output many times over. A quasar is essentially the blazing, overactive core of a young galaxy, where a supermassive black hole is consuming surrounding matter at an extraordinary rate. Whatever material the black hole cannot immediately swallow spirals around it in a colossal accretion disk, accelerating close to the speed of light and heating up to millions of degrees through friction alone. That process alone can outshine an entire galaxy of 1 billion ordinary stars, making quasars simultaneously among the most massive and most luminous single objects known to exist. Normally, the light from an active quasar can be observed clearly across billions of light years, but the dense gas surrounding these particular objects absorbs most of the shorter, bluer wavelengths, letting only longer infrared light escape. That filtering effect is exactly what disguises a raging quasar as nothing more than a faint red dot in Webb's images. According to astrophysicist Dale Kochevsky, one of the researchers involved in this line of study, the accumulated evidence points strongly toward this conclusion, that many of these little red dots represent the very first generation of supermassive black holes ever detected forming in the young universe. That raises an entirely new mystery, though, because quasars are supposed to form and grow gradually inside the centers of already established galaxies. If massive galaxies hadn't yet had time to assemble this early in cosmic history, how could fully formed supermassive black holes already be sitting at their centers? The answer scientists are now exploring suggests that the earliest universe may have played by an entirely different set of rules than the one that governs black hole formation today. In the modern universe, a black hole typically forms through the death of a massive star, an explosive supernova whose brightness can briefly outshine its entire host galaxy, collapsing inward to leave behind a compact black hole that then spends billions of years slowly consuming its surroundings and growing larger. But data gathered by Webb suggests the very first supermassive black holes may have skipped that step entirely, forming directly from the gravitational collapse of enormous ultra-dense clouds of primordial gas without ever passing through a supernova stage at all. Once formed, these so-called direct collapse black holes would have aggressively consumed the surrounding gas, growing rapidly while their gravity simultaneously helped pull together the material that would eventually become their host galaxy. In effect, it looks as though the young universe built its monsters before it built the neighborhoods meant to contain them. While continuing to study this early era, Webb uncovered another disruptive and violent process at work, one capable of killing off young galaxies almost as soon as they began to thrive. To sustain the ongoing formation of billions of stars, a young galaxy depends on a steady supply of cold hydrogen gas, and in the early universe, that raw material was abundant which should have allowed the first galaxies to flourish uninterrupted for billions of years. Instead, Webb's observations revealed something far stranger: galaxies whose star formation abruptly stalled at what should have been the peak of their youth. This phenomenon has been studied closely by a team led by astrophysicist Rebecca Davies from Swinburne University of Technology in Melbourne, who examined a distant galaxy known as Cosmos 10142, sometimes nicknamed the Cliff, and identified an almost unimaginably powerful galactic outflow tearing through its center. This is not an ordinary cosmic wind. It is a dense, violent surge of cold molecular gas erupting outward from the galaxy's core at speeds reaching hundreds of miles per second, carrying an almost incomprehensible amount of kinetic energy. Had our own solar system somehow found itself in the direct path of a flow like this, any planetary atmosphere caught in its way would be stripped away almost instantly. Davies has compared the densely packed regions of the early universe to overcrowded, chaotic megacities, where galaxies constantly collided, merged, and triggered explosive bursts of star formation, operating under an almost reckless philosophy of burning bright and burning fast. But that same intensity ultimately became the galaxy's undoing. The extreme density at its center produced waves of massive stars that burned out almost immediately, triggering a cascade of supernova explosions whose combined shockwaves swept up the surrounding hydrogen and hurled it out into deep space at a rate roughly twice as fast as the galaxy could convert that same gas into new stars. The galaxy was effectively suffocating itself, blasting away its own fuel supply with no realistic way of reclaiming it. Based on the observed rate of gas loss, researchers estimate this particular galaxy may exhaust its star-forming material within the next 50 million years, an astonishingly short span in cosmic terms. And because we are viewing this galaxy through light that has taken roughly 12.8 billion years to reach us, whatever is truly happening to it right now remains completely unknown to us, hidden somewhere in a present we simply haven't received the light from yet. While much of Webb's most disruptive work has focused on the distant, ancient universe, some of its most surprising recent discoveries have come from something far closer to home, and in some cases, moving directly through our own solar system. In the summer of 2025, the NASA-funded ATLAS survey telescope in Chile detected a comet that had clearly originated from outside our solar system entirely, arriving from the direction of the constellation Sagittarius. Astronomers named it 3I Atlas, making it only the third confirmed interstellar object ever detected passing through our cosmic neighborhood, following the strange cigar-shaped Oumuamua in 2017 and the comet Borisov in 2019. Unlike the relatively inert Oumuamua, 3I Atlas arrived trailing a visible cloud of gas and dust, behaving very much like an active comet, which made it an unusually promising target for detailed study. As 3I Atlas swung around the Sun and began its journey back out of the solar system in late 2025, Webb turned its mid-infrared instrument toward it and captured something astronomers had never observed on any interstellar visitor before: clear evidence of methane gas. This was a genuinely surprising find because methane is an extremely volatile substance that should have boiled away long before the comet ever got close enough to the Sun to be studied this closely. The fact that it survived suggests the methane had remained sealed deep beneath the comet's surface crust for untold ages, shielded from solar radiation, only becoming active once the Sun's heat finally penetrated far enough to reach those buried reservoirs and trigger fresh jets of escaping gas. Webb's data also revealed an unusual chemical signature, with methane and carbon dioxide present in proportions noticeably different from what's typically seen in comets that formed within our own solar system. A strong hint that 3I Atlas formed under very different conditions, likely around a completely different star, in a colder and more distant environment than the one that produced our own sun and planets. Based on these measurements, researchers estimate this particular chunk of interstellar ice may have formed somewhere between 10 and 12 billion years ago, meaning the star system, where it originally came together, may no longer even exist. In effect, scientists have been given a rare opportunity to study a wandering time capsule that could be nearly as old as the observable universe itself, and its unusual chemistry has already demonstrated that the rules governing planet and comet formation elsewhere in the galaxy may look nothing like the ones that shaped our own solar system. When this interstellar visitor made its closest approach to Earth in December 2025, understandable public excitement briefly spiraled into online panic, though its trajectory had placed it safely away from our planet from the very beginning. The same could not initially be said with total confidence about a very different object, an asteroid known as 2024 YR4, first spotted by the ATLAS survey system in Chile in December 2024. Roughly the size of a 10-story building, somewhere between about 174 and 220 feet across, this asteroid quickly earned the nickname City Killer among planetary defense researchers, because an object of that size, striking a populated area, could level a city and leave behind a scorched, crater-marked wasteland. Early tracking data was alarming enough that the asteroid briefly reached a Torino scale rating of 3, the second highest impact hazard classification any real asteroid has ever received, trailing only the brief, later downgraded scare surrounding asteroid Apophis back in 2004. As astronomers gathered more observations through early 2025, the odds of an Earth impact were ultimately ruled out entirely. But a strange complication emerged in their place. The improved trajectory data suggested a rising probability that the asteroid could instead strike the Moon on December 22, 2032, with estimates climbing as high as 4.3%, an unusually high number for a lunar impact scenario, and enough to keep planetary defense researchers watching closely. The problem was that 2024 YR4 then became too faint and too distant for any ground-based or space telescope to reliably track, and astronomers expected they would have to wait until 2028, when its orbit brought it back within observable range, before gathering any further data. Instead, a team led by planetary astronomer Andy Rivkin identified a narrow observational window in February 2026, during which Webb, and only Webb, might be sensitive enough to catch a brief glimpse of the asteroid using extremely precise reference stars, mapped by the European Space Agency's Gaia mission. Webb succeeded, capturing the extraordinarily faint object on both February 18th and February 26, 2026. An object so dim it reflected roughly as much light as a single almond would if placed at the Moon's distance, several billion times fainter than the faintest stars visible to the naked eye. By comparing the asteroid's precise position against Gaia's meticulously charted background stars, researchers narrowed the uncertainty in its future trajectory by roughly 12-fold. The final result, announced in March 2026, definitively ruled out any chance of a lunar impact, with the refined calculations showing 2024 YR4 will instead pass the Moon at a safe distance of approximately 13,200 miles. What had briefly looked like a real, calculated threat to our nearest celestial neighbor was resolved entirely thanks to the same telescope currently rewriting our understanding of the universe's age, its earliest galaxies, and the forces shaping its ultimate fate. Taken together, these discoveries paint an extraordinary and genuinely unsettling picture of a universe that behaves very differently than the tidy, predictable model most of us grew up learning. A universe expanding at two measurably different speeds depending on how and when you measure it. A universe where supermassive black holes may have formed before the galaxies meant to contain them even existed. A universe capable of building young galaxies so violently that they end up destroying themselves within tens of millions of years. A universe that occasionally sends ancient alien fragments of ice drifting silently past our own planet, carrying chemical signatures from star systems that may no longer exist at all. And even our own cosmic backyard still holds surprises, faint, distant rocks whose futures had to be painstakingly rescued from uncertainty using humanity's most powerful telescope. Every one of these findings traces back to the same underlying truth, that the universe we thought we understood, built on a century of careful observation, since Edwin Hubble first noticed those retreating galaxies, may only be a rough sketch of something far stranger, far older in places, and far more violent than anyone anticipated. And as Webb continues staring deeper into the past and further into the dark corners of our own solar system, it seems increasingly likely that the biggest revelations and the biggest challenges to everything we think we know about the cosmos are still waiting to be uncovered.